turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast. This is the show that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. With me, Chris Smith. And coming up this week, stranded NASA astronauts Butch Wilmore and Suni Williams come down to Earth not with a bump, but with a splash and some awesome drone footage to boot. Also, Cambridge scientists are mapping where you can find the world's rarest minerals. We'll talk to them and find out why and how. And the massively underappreciated role that whales play transporting nutrients thousands of miles using just their urine.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
We begin today's programme with the long-awaited return of astronauts Butch Wilmore and Suni Williams down to Earth. The pair had been stranded on the International Space Station for 9 months. Let's hear a bit of their descent back down to the Florida coast.
All hooks open.
All hooks are open. And undocking confirmed. Freedom is free of its moorings. Suni Williams and Butch Wilmore begin their belated trip home.
Separation confirmed.
Houston Station on the Big Loop, Step 2, ISS thrusters are verified, enabled. To Crew 9, safe journey home. It's been the honor of a lifetime to cross your path up here on Space Station. Your service has been very much appreciated, and we'll miss you, but have a great journey home.
and splashdown. Crew 9 back on Earth.
Some wonderful narration of Butch and Suni's return to Earth. We're going to get a quick word now from the space scientist and author David Whitehouse. That is a wonderful conclusion to it all, isn't it, David? But what is the story behind this story?
You're right. This is a remarkable conclusion to an incredible episode in the exploration of space. There's hardly been anything like it before. Butch and Suni were going up last year for an 8-day mission to check out the Boeing Starliner capsule, which is, on paper, a very able and capable capsule designed to work alongside Elon Musk's Dragon capsules to take people to and from the space station. But they had problems with it when they were docking, the thrusters, the insulation, and it was deemed unsafe to bring them back. Although it did return in an uncrewed mode, it left Butch and Suni on the space station with problems as to how long they're going to stay and how they would fit into the natural rotation of crews going up and down. And they had to transition from being a visitor to being a long-term space station crew member and await their ride home, which we've just seen has been, actually, I should say, among the most spectacular, sharp, high-definition, close-up images and video of coming home I've ever seen.
One thing that wasn't entirely clear to me was why there was a problem getting them home and why their 8-day stay turned into more than 8 months in space. Why couldn't they just send another spacecraft? Or there are spacecraft going all the time to the International Space Station, aren't they? Couldn't they just make some space on one of those and bring them home sooner? What was the hold-up?
There were several problems. First of all, I think Butch and Suni were not unhappy that they were spending longer in space, because these were their last missions. They'd been on the space station before. And as a finale to your space career, seeing more sunsets and actually being in space is what astronauts do. They were not heartbroken not to be coming back quick, although the time did drag on, I think, towards the end. The problem is there is a regular schedule of spacecraft going up and down. There are only a number of docking ports that you can use. Part of those capsules are Russian, part of them are American. In order to keep the crew rotated, keep rookies coming up for their experience in a space station, which has only got a few years left, they didn't really fit in for several months. Now, there is a bit of an argument going on that Elon Musk said he could have sent a capsule up to bring them back in September or October, but that the Biden administration and NASA didn't want them to do that because it would have handed a political goal to Donald Trump. It didn't happen. They had to wait for a Dragon capsule, and there were complications in the sense that their spacesuits that they wore inside the Starliner were not compatible with them coming home on a Dragon capsule. So they had to have new spacesuits designed and built down on the ground and then taken up and then tested. So one thing or another, it was easiest to bring them back at this time. And this was a decision to bring them back now that was actually made before Trump was elected.
What's the nature of that return journey? When you've been, what is the trip back like, and how long does it take, etc.?
Depends upon how you come back. In an emergency, if you come back in a Soyuz, you can actually be back on the ground within an hour and a half, having pressed just one button. But in order to make the return in the Dragon capsule a little easier and to bring it down in the Gulf of Mexico, I don't know what I'm supposed to call it these days, off Tallahassee, off Florida, they had to stay in space for 18 hours after they had undocked to do various orbital maneuvers and check out the spacecraft and things like that. But really, the return's very automatic. People know when to fire the rocket motors, in which direction, for how long, how the speed is going to be slowed down. And testimony to that is that when the Dragon capsule came down to splash down, SpaceX was already able to put a drone almost exactly in front of it to watch it come down. And the pictures were incredibly remarkable and testimony to the accuracy at which this process can take place. But of course, getting back is one thing. It takes a while to adapt to being in zero gravity when you go up there. Then after 9 or 10 months of that, to come back and within half an hour be hit by full Earth gravity for the first time in almost a year, that is another thing entirely. That is tough.
Apart from that, which is going to take a bit of rehabilitation, isn't it, for them to get their strength back, etc.
Mm-hmm.
What have they said, or what have been the reactions of the two of them?
They're very glad. Sunny's back, glad to be back home. She's missing her dogs, evidently. They haven't issued any public statements since they've got back, but they have said how happy they are to be back and how their bodies feel like concrete when they're trying to move around. And their first night back must be very difficult in Earth gravity on a proper bed. So we've yet to hear from them in a press conference. They've weeks of rehabilitation ahead of them and constant monitoring for the rest of their life because of the exposure to radiation they've had in space. So we'll hear their story. And I bet there are publishers out there who are desperate to get hold of the publishing rights for Butch and Sunny's own story of their prolonged stay in space. We'll hear about it soon.
You've written a few space science books in your time, haven't you? So I suppose that in fact it might not just be publishers, it might be Hollywood that come knocking as well. It's got Armageddon Mark II and that kind of thing written all over it, isn't it? It's a great story.
I don't know if Sunny and Butch have got agents. If they haven't, they should have, because they have experienced one of the most extraordinary episodes in space exploration, which has got politics, space flight, it's got technical details, it's got so many interesting things. And yes, books, Netflix videos, documentaries. These astronauts think they're retiring.
Go on, say it, David.
Not.
The sky's the limit.
The sky's the limit.
Space science journalist David Whitehouse there. Now, in recent times, smartwatches have been shown to be able to detect the onset of viral infections some considerable time before obvious symptoms of illness appear and are apparent even to the victim. But now, new research suggests that beyond just alerting the individual about their potential impending problem, these devices might be able to help stop a pandemic in its tracks. I've been speaking with Mart Versonen from Aalto University in Finland.
We already knew from research that wearable devices, and specifically smartwatches, are able to detect infection before any sort of symptoms, so sneezing or coughing, start. We sort of asked ourselves, how much of an impact can it have if we were to use these devices in pandemic management and people were to sort of change their behavior given a smartwatch alert?
And what are the smartwatches are responding to? When we look at them and we can say, yes, this person is infected with something, what's the giveaway that the watch is able to pick up on?
Yeah, so I guess the most common ones, of course, are the body temperature, heartbeat, heart rate variation, and then blood oxygen level. So those are like the most common ones, I would say. And
that, crucially, changes before a person may even be aware that they've got something.
Yeah. So likely, even with the most basic devices, you would see an increase in your heart rate, for example, just before you start showing symptoms.
Because one of the things that caught us out with the pandemic was initially we assumed that if you weren't symptomatic, you weren't infectious. Obviously, if we get prior warning that someone might be infected with something before they realise, you could take action sooner. Is that where you're coming from with this?
Exactly. And actually, we also know that a significant amount of the sort of infections to other people come from before you actually show any symptoms. So that was especially problematic with COVID, for example, because the incubation, all of the time between you getting infected and actually showing symptoms was so long that you had quite a while to infect other people before you actually realized that you yourself were infected. So if we can hit really sort of that mark, we could have a huge impact on how pandemics develop.
So take us through what your parameters were. What fraction of the population would have to be using a smartwatch, did you assume? And what sort of a difference, if they did, would it make to the trajectory of a problem like COVID?
The proportion of people using the smartwatch was actually sort of merged together with a parameter we called reduction in social contact. So if you get the prompt, how much would you reduce your social contacts? And that's essentially very similar to, saying if you don't get the prompt because you don't have a smartwatch, you just wouldn't reduce contacts at all with the smartwatch. There's some other parameters that we used was the development of the viral load, so the amount of the virus in the human body for these different diseases. We also looked at previous research on how early the wearable devices can detect certain diseases. One very sort of important part of the study was also that these smartwatches can catch people who are also asymptomatic completely. So there's 20-something% plus or minus something in many diseases where people infect other people but show no symptoms at all. And those are also something that is possible to catch with wearable devices.
Taking all that into account then, if we did have COVID Mark II tomorrow and smartwatches in the population, what sort of a difference could this sort of intervention make, do you think, based on your simulations?
I think it would be a really big difference, but it of course depends. For example, we looked at 3 different variants of COVIDs. The very first one, for example, we could have almost eliminated in sort of very realistic contexts. If we were very optimistic, we could eliminate almost everything, but keeping realism in mind. But on the other hand, then we looked at Omicron, which was really infectious. And so for that case, the most likely outcome would be sort of flattening the curve, as to say.
It's going to make a difference, though, on the demographic of the country and also the living conditions, isn't it? Because one of the arguments made was that in countries like Sweden, where the approach was a bit different to countries like the UK, people said, well, hang on a minute, the density at which people live in Sweden is very different than, say, the density at which people live in London. And so if you're wearing a smartwatch, it makes no difference whatsoever if you go home and infect all your housemates.
That's of course true, but then again, assuming that if you get the alert even one day before, you could make the decision to stay at home and not, follow up with a visit to your grandma, for example, or the store, or if that's an option to you, you could work from home. So there's a lot of these decisions that you yourself could make given that extra information. You could still reduce the amount of extra infections by making, better decisions, or at least more well-informed decisions.
So do you think policymakers should be listening to you and saying, well, this should be part of our pandemic planning for the future?
I definitely think that policymakers should consider it part of their toolbox, because that could have a huge impact on how we manage pandemics. I think that there are, of course, ethical considerations always when any kind of government or also centralized data collection is even passes someone's mind. But even say, in a situation where I voluntarily go out and buy myself some sensors or a smartwatch, have that go to my phone, and based on that, infect less people, I think that policymakers should be at least aware of this possibility.
Mark Versenum at Aalto University in Finland there, and that study has just come out in PNAS Nexus.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientist podcast with me, Chris Smith. On the way, how whales move nutrients thousands of miles using just their urine. Before that, though, we're examining minerals now. Now, not only are they incredibly valuable, but they often are at the heart of global power struggles. The Democratic Republic of the Congo, for example, is home to more than 70% of the world's known cobalt and a major battleground of competition between the United States and China. Meanwhile, Ukraine's lithium and titanium reserves could form part of a future peace deal between Moscow and Kyiv. So knowing where these deposits are really matters. And researchers at Cambridge University have been busy mapping them, and they've found a useful way to predict where they all are.
My name is Sally Gibson. I'm Professor of Petrology and Geochemistry in the Department of Earth Sciences at the University of Cambridge. Where I brought you to are the mineral galleries of the Sedgwick Museum, which are in the University of Cambridge. And I really brought you here to sort of set the scene for the research that we've been doing.
Which is what?
Which is looking at the distribution of volcanic rocks on our planet's surface and how they relate to its deep geology.
Why is this a thing? Why is this important?
Well, it's important because we still have large gaps in our understanding as to the relationship between the deep structure of our planet and what happens on its surface.
I thought that had been figured out, going back over 100 years by Mohorovičić in Croatia, because he was using seismic waves to see inside the planet even then. I've seen his notebooks. What still remains then for us to try and unpick?
Well, yes, that's absolutely true. But what we're able to do now is to use recent advances in the number of seismic stations, and these allow us to put together much better 3D impressions as to what's happening within our planet. And what we can do is we can build up maps, and we can correlate these with the surface distributions of volcanic rocks and of mineral deposits.
In essence, then, just as Mohorovičić did, you're using waves from earthquakes going through the Earth to figure out the structure inside. But how does that tell you what it's made of?
It's a multidisciplinary study that we're doing. So we're working with geophysicists, and we're combining information on the chemistry and the mineralogy of the Earth and building up this comprehensive picture as to what it's made of and how it varies with depth. What we really want to know is what controls where we have things such as volcanic activity, where we have mineral deposits. How does this relate not to surface geology, which is what people have traditionally been doing, but we want to explore deeper within our planet.
And what are you finding?
We found some really exciting information about how the thickness of the lithosphere, this is our planet's rigid outer shell, how this varies across the continents. And when we superimpose onto these maps of lithospheric thickness the locations of volcanic rocks and also these mineral deposits, we see this really systematic relationship. It's a relationship that's not possible by just looking at the surface geology. We're looking at things that are happening hundreds of kilometres within our planet.
What is that relationship, and what's the giveaway?
The big take-home message that the cores of our continents are made of really thick lithosphere. These are thick roots that are extending down into the interior of our planet, but these have steep margins, and it's on the steep margins of these regions of thick lithosphere is where we're finding these volcanic rocks that are associated with some of these really important mineral deposits.
Have you therefore now got effectively a map of all the juicy places for the best minerals on the planet? Is that what this is going to lead towards?
Well, what we're doing is we're building up these maps, and our project is for 3 years. And what we're doing is we're gradually increasing the resolution of these maps so that it will enable us to better pinpoint where these mineral deposits occur, but also critically for us will increase our scientific understanding as to how they form and why they occur in certain locations.
Will this be of interest to mining companies then? Because they would look at this map and say, well, these look like good areas that previously we hadn't considered or have been underexploited, and your maps are pointing towards these areas being a rich source.
Yes, absolutely. So, there are places that are really hard to access, that these deposits haven't been found. So the particular volcanic rocks that are associated with these mineral deposits, they are relatively small in terms of their surface outcrops. They're less than 1 kilometre, so they're not that easy to locate on a continent scale.
Could there be a tension, though? Because inevitably, out of work like this will come predictions about parts of the Earth that we value very highly for, say, biology, biodiversity, conservation, and so on, and it might put the industrialists at odds with the conservationists.
Yeah, so I think it's really important to emphasize the scale of our study. So the resolution of our study is on the scale of hundreds of kilometers. So although we're looking at global relationships, it won't actually sort of pinpoint a very specific location. And our interest in this is really as scientists trying to understand more about how our planet processes these elements and how they reach our planet's surface.
So if you put someone onto a real winner and they make a fortune, are you going to get a kickback?
That's probably
strike gold.
That's probably highly unlikely. You know, we're very much doing this from a scientific perspective.
But money makes the world go round. You've got to pay for your research somehow. Seems reasonable to me. There's some data points you've left off the map, Sally, so that you can then go up to the industrialists and say, there's a really good one that I haven't put on the map.
I think we'd really like to embrace the findings that we have with other stakeholders, and this is really part of our project. We're at a preliminary stage now, but we're very keen to reach out to other people and see how our findings can be used in a broader context.
Sally Gibson talking to me at the Sedgwick Museum of Earth Sciences in Cambridge. Well, now we're going to quite literally take the pee, whale pee, because the study has found that these huge mammals play a massive and previously unrecognised role in moving literally thousands of tons of nutrients, foremost among them nitrogen and phosphorus, which are essential in sparking plankton blooms over thousands of miles of ocean. This creates a nutrient cycle on an epic scale, as they feed in one place and then they relieve themselves, as well as reproduce and die, in the process delivering nutrients, in another. The University of Vermont's Joe Roman has made the discovery by studying the habits of humpback, right and grey whales. And don't be under any illusion about how much urine we are talking about here.
So a typical human, we make about 2 liters of urine a day. Fin whales are much larger, so that's the only species that's actually been studied, and this is from whaling data in Iceland. Estimates are maybe 1,000 liters or 250 gallons per day, and similar amounts for other large whale species. And that is rich in nitrogen. It's also rich in other nutrients like phosphorus. And then it also has chlorine and sodium. And for your listeners, realize that's pretty common, right? In the ocean. So we really looked at the nutrients that are limiting, that are going to spark growth in those areas.
And so to what extent might they therefore be moving nitrogen around rather than just they pick up nitrogen in their food from a local area and then they just pee in that local area, so they just cycle what's already there around? Have you got evidence they're actually actively moving the nitrogen from A to B?
Whales are what's known as capital breeders. What does that mean? It means they feed for part of the year and they breed at a different part of a year, unlike humans, which have to feed all while they're having offspring. So they're traveling 1,000, 2,000 kilometers to places like the Caribbean or Hawaii. And the females, in order to give birth and in order to lactate and to gestate, they need enormous amounts of energy. Where do they get that from? They're breaking down the fats and the proteins that they stored in the summer. And in the process, they have to release excess nitrogen, excess phosphorus. Other pathways include placentas. So whale placentas can be hundreds of pounds. Infant mortality in whales can be fairly high. So when a calf dies, that brings a lot of nutrients. And then the whales themselves can also, they can die on the breeding grounds as well. So those 4 pathways are how they bring nutrients. But because whales are peeing all the time, that's the main source by far, is the urine, is the main source for nitrogen and other nutrients.
So how much nitrogen are they moving and other nutrients around the planet when they go from A to B in this way?
About 4,000 tons of nitrogen per year. So what we did is we looked at one particular system, whales that feed in Alaska and breed in Hawaii, because that system's well studied. There, they bring as much nitrogen from Alaska to Hawaii as the local processes of wind and upwelling transport into these systems. So this is a biotic or a biological form of bringing these new nutrients, these external nutrients, into the system. And then we start to get an idea of what the impact might be on phytoplankton. Hawaii, about 4,000 tons of biomass, or just body, are transported there every year. And that's comparable to like 10 million Big Macs. I mean, they're bringing a lot of food into the system. So it's not just the nutrients, but sharks feed on the carcasses or the placentas, fish feed on it. These nutrients can get into the coral reef systems. So it's two processes, one sort of daily in the urine and the other in, at the end of an animal's life is the other big pulse of nutrients or biomass food.
Did we see an impact then when there were fewer whales? Luckily, numbers are climbing across many species because of international bans on whaling. Wasn't always like that, and some animals were close to the point of jeopardy. They have rebounded. So are we now seeing a change in that nitrogen flux? And what impact, if so, is that having?
That's exactly right. So historically, whales it depends on the species. We haven't talked about blue whales and fin whales, but blue whales, for example, were reduced to about 1%. Largest animals ever existed on the planet, down to 1% of their population in the southern hemisphere. So basically, they had no ecological role. And that still sadly remains for some species, like the North Atlantic right whale. Only 350, 400 whales on the planet. Their ecological role is pretty small. Let's look at some better news, though. Right whales in the Southern Ocean, as well as humpback whales in the North Pacific and gray whale populations have all increased. They're rarely up to historical numbers, but that has allowed us to really examine what the impact of these whales could be. I think 50 years ago, 60 years ago, oceanographers overlooked the role of whales. They were so rare. Of course they weren't important. We had basically eradicated them. But keep in mind, Chris, that we still have a long way to go here. One study that we mentioned is 4% of the biomass of mammals on the planet is wild biomass. The vast majority is humans and cows and sheep. That 4% includes all the whales, all the great whales. So it's not surprising that we haven't considered animals as being as important part of what I describe as the circulatory system of the planet, because we really sort of clogged up those arteries. And now we're just starting to see in places like Hawaii and the Caribbean what the restoration of these species can mean for local ecosystems and for global nutrient transport.
It's an amazing story, isn't it? The University of Vermont's Joe Roman there. That study has just come out in Nature Communications. Well, we're staying at sea for our question of the week this week, and James Titko has been examining what happens to some heaps of rubbish highlighted by one of our listeners.
It's Silke contacting you from French Polynesia, where I'm currently living and cruising on my boat. Like many other cruisers, I collect garbage that has washed up on the shore, and my question is, what is best to do with it? The locals here in the atolls mainly burn it. The garbage consists mainly of various types of plastic. Is this environmentally the best option to deal with it? Thank you so much.
Hi Silke, thanks for the question. Burning plastic waste, especially in open fires, is not the best option for the environment. It releases toxic chemicals in the smoke, such as dioxins, furans, and other harmful pollutants, which can be seriously damaging to human health and the environment. Here to tell us more and help you find a solution is Richard Lampitt from the National Oceanography Centre.
Thanks, James. As you say, dioxins and furans in particular are really toxic and can cause cancer, skin disorders, liver problems, and damage to the endocrine and immune system. In contrast to the plastic itself, it's actually the additives which are most concerned, such as plasticizers, stabilizers, and flame retardants that are released on burning. In addition, since plastic is made from oil and gas, i.e. fossil fuels, for every ton of dense plastic burned, up to 2 tons of carbon dioxide is released into the atmosphere. Really bad news for global warming. The part of the world you're writing from, Silke, also has plenty of marine life, and the toxins from burnt plastic can negatively impact them too.
Usually when we talk about plastic pollution, primarily the answer is to reduce, reuse and recycle. But in your case, Silke, where much of the plastic you'll be coming into contact with will likely be from elsewhere, this mantra which we all aspire to may not be so relevant. So what can you do?
Secure disposal in proper landfill would have a slightly less harmful impact on the environment, but refuse sites often catch fire, so the effect on the environment is similar. Incineration at really high temperatures, above say 850 degrees centigrade, is the most effective method for destroying organic chemicals such as dioxins and furans. And a process called pyrolysis does exactly that. The plastic becomes a gas which is then burned as a clean fuel, free of pollutants, generating electricity. The major drawback, however, is that these are really expensive infrastructures to build and then to run. So, what about other solutions? Another plan is to shred these plastics directly on site and transport this material to Tahiti, where there's a growing recycling facility. Tahiti has the most sophisticated recycling system in the Pacific, but still exports quite a lot of garbage.
It seems there are no easy answers to your question, Silke, but burning plastic on open fires is not advisable. Collecting the rubbish you can and delivering it to waste management facilities sounds like your best bet, but it all goes to show that the fantastic properties of the plastics we use in our daily lives are also the main reason they pose a huge problem to our environment. Thanks to Richard Lampitt from the National Oceanography Centre for helping us with the answer. Next time, we'll be answering this question from listener Francisco, all the way in Chile. He writes, I've been told that jumping on a trampoline is healthy for humans. It's considered as good exercise and also helps coordinate brain and body. I'm 73 and wondering whether it's advisable for me to jump on a springboard.
And do be sure to drop us a line if you know the answer to that one, or if you've got a scientific corker of your own you'd like us to put under our microscope. You can send your questions in to me now. It's chris@thenakedscientist.com. And of course, if you're interested in more on this and other topics, then why not tune into our recent show, if you haven't already, on microplastics. We'll also be giving air pollution a closer look in the coming weeks as well. That's all we've got time for in this episode. Thanks again to those of you who are stepping up and making donations to help support the programme. That's at nakedscientist.com/donate. Some of you are very, very kind and are supporting us on a regular basis. Others of you in a one-off capacity. We are extremely grateful to all of you. Again, if you can help us and you'd like to do that, you go to nakedscientist.com/donate. We really appreciate it. The Naked Scientists will be back next week when we look at antimicrobial resistance, otherwise known as AMR, when we're going to be leaning on the expertise of members of UCL's Digital Health Hub for antimicrobial resistance. What are they doing to try to combat a massive global challenge? The Naked Scientists comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith. Thank you for listening, and until next time, goodbye.